What is discrimination, or what are discriminators? The idea here is that it is actually possible to do a lot of things in linear time that you have sort of brainwashed yourself into accepting take n log n or n squared time. Okay, and what I want to do is showcase how we can package that up, how we can turn it into a library, how we can make it accessible so that people can use it. This is a bit of a case study in sort of library design in Haskell, at least the way I approach it. Sort of going out into category theory and trying to grab little bits and pieces and drag them back and kicking and screaming and make them work, while not being afraid of going down and building a custom foreign prim to do whatever the heck it is that I need to make fast. So we'll be kind of flitting around at different levels of abstraction in the Haskell ecosystem. How many people here don't know Haskell? Okay, I apologize. How many people here don't know what a radix sort is? Let's start there. Okay. So the idea of radix sorting is that there's a really fast linear time sorting algorithm for integers. What you do is you could start by just making a one bucket per integer, and then when you go to take the next element out of your list, you put it in the appropriate bucket, then you run through all the buckets in order, and you glue together the answers. Right? This would be a really naive version of a radix sort because it's using way too many buckets. But if you had something like 32 bits worth of integer, that would be an awful lot of buckets. You probably don't want to go there. So it turns out what you could do is you can actually like grab like 8 bits. You can only have, if you only had like 256 buckets you could put your lists into. You could thread by the least significant bit into there, then by the next, by the least significant byte there, then the next most significant byte, then the next most significant byte, and then the next most significant byte. By the time you were done, you would have sorted your list, and it would only have taken you 4 steps and constant time. Or sorry, not constant, linear time. Okay. In around 1990, Burke and McIlroy, was it? I think did a paper on how to make radix sort fast, because radix sort was a nice historical curiosity at the time. But quicksort was kicking its butt even despite the fact that it was linear. The constants were just too bad. And so they came up with this technique that has sort of retroactively been called the American flag sort, which was an unstable radix sort that could extend it to support some other cases. And the key observation here is that we're able to break the sort of expected, theta n log n bound on sorting. You've had it drilled into your head that sorting takes n log n no matter what you do. And we're able to break that bound because we're not working pairwise. We're not comparing 2 elements, are you less than this, and then going from there, which provably requires n log n comparisons. But instead, we're able to abuse the fact that we have a whole array full of buckets, and we can just shuffle things into the right buckets. And so we can work kind of wholesale through our data structure. So that's the idea of a basic radix sort. Now, radix sort worked bottom up from the least significant bits up, and American flag is a slight tweak on that to work top down. So again, the key here is that what I want to show is that we can do almost everything we want to do in linear time, and that includes sorting, partitioning our data into equivalence classes, joining tables, so we can actually stream. We can not stream yet, but we can take a whole data set in for 2 sides of a join that we want to be able to compute, break them up to where the 2 things agree on the key, or whatever the column is that you're joining on, and spit out the result, and it's linear in the total amount of input and the total amount of output. We can also construct data.map and data.set in linear time using this technique as well. And so I'll get to all of those individual pieces. I'm just trying to motivate why we care, right? So who, what, why, when, where. So why is that we want to be able to do almost everything in linear time. Who is this dapper fellow here, Fritz Henglein. He runs the Hyperfit Research Center at the University of Copenhagen. He came up with this idea. He wrote a bunch of papers between about 2007 and 2011. It's pretty much entirely his baby. And he's got some wonderful papers on the topic, and they're very accessible. probably far more so than this talk. However, in some ways, they're not very Haskell-y. Like, he builds up data types directly for working with all the things that he wants, but then he doesn't get to use any of the classes that we know and love to work with them. And so a lot of what I want to explore today is how to build a nice API that feels good to a Haskell programmer to use. And so I'm going to take his encoding and turn the whole thing around and see if we can get to something nice. And so, again, I'm out to build a nice API. And to get there, I'm going to start with the notion that monads are monoids in the category of endofunctors. What's the problem? I probably should have talked to you about doing this on the second day after Ken had had a chance to give his intro to category theory talk. Sorry. So maybe this will motivate some people to attend your session. Maybe it'll send them screaming. I'm sorry. So in Haskell, we have a monoid as a very basic class. You have a binary operation and a unit for it. The binary operation is associative. We all know that. But how does that fit into the monads or monoids notion, right? And for that, we need a better notion of a monoid than this simple little piece. And so, as all things categorical do, in order to get to just a little bit more complicated, we have to go way more complicated. We build up the notion of a monoidal category. So how many people here know what a category is? How many people don't? All right, sorry. A category, in very broad strokes, is you have a set of objects and a set of arrows between objects. So you have arrows that connect from one object to another object, and you have the ability to compose two objects together. And it doesn't matter if you compose from here to there and then to a third thing, which order you kind of compose the arrows, you get the same arrow. So arrow composition is associative. Okay, it's like a really fancy form of a monoid. You have the associativity, and you have this extra thing, which is that for every object, you have an identity arrow, which acts like the unit that we had for our monoid. Now, a monoidal category is a category equipped with some extra stuff. Okay, so one of the things that we work with a lot when we deal with categories is that we have functors between two categories. A functor is a mapping from one category to another category where if something was connected over here in a nice way, it carries over the shape. So a monoidal category is a category where we have a bifunctor, a tensor, something that looks like product. It's also going to look like coproduct in a bit. We're going to play with this. There's a bunch of things that all fit into this mold. And we have some object that acts like an identity for this bifunctor. So that if for any element A, every object in the category, A tensor I is equivalent to, there's an isomorphism between that and A. You can go back and forth between this representation and that, right? So if you think of this as products in Haskell, we have the pair of A and the unit is isomorphic to A. We have no extra information in that unit. There's only one inhabitant of that type, so it doesn't really add anything to the equation. And these are traditionally denoted R and L, rho and lambda for right and left, because mathematicians like to screw with people. And A for associativity, which says that we can slop our bifunctor from one side to the other. So we can say A tensor B tensored with C can be turned into A tensor B A tensored with B tensor C, and vice versa. You can go back and forth. So putting on and taking off the unit doesn't create or destroy any information, and you can associate, which doesn't create or destroy any information. Okay, so this is all the things you can do with products without ever potentially forgetting something or reusing something. And then you get these crazy diagrams. And this basically says that these don't do anything hinky, and no matter how you get from everything being associated all the way to the left to everything being associated all the way to the right, it doesn't change the answer. Okay, so McLean came up with these things way back in the 50s or the 60s, and then Knuth and Bendix figured out how to do a bunch of things like way, way later, and these actually turned out to be exactly the right conditions under far more general conditions than McLean could have ever known. So, so this is the notion of a monoidal category, which is the beginnings of like where category theory starts to become interesting. Okay, so why do I need this thing? So the first thing we want to talk about is like Haskell itself as a category. We can say that Hask is a category where our types are objects, and functions between those types are my arrows. So I can now compose two functions and get an arrow that goes from the source object all the way to the target, skipping the middle point. And then we can say that product is this notion of a tensor that we're going to use, and that the unit object is going to be the unit of our product. And so row could put on or take off a unit, or an identity here on the right-hand side. So it has to be the first function. It projects out the A and leaves the unit alone. And then the inverse version of it is that we just take whatever A you give me and we shove it in and we create a unit. You can sit down and prove that those are inverses. We have lambda does the same thing. I don't think, just on the other side. I leave this as an exercise for the reader. We can also do other choices of tensor. We're not limited to just doing products, and this is where things start to get interesting and where we can start to see a more general notion of a monoid once we go through just a couple more steps. And that is that either, I'm going to use plus here because notationally it fits on the slide. With void being the uninhabited data type also works. So we can go from either A or nothing, basically void, to A by just projecting out the left-hand side, because you know the right-hand side can't happen. It's void. It's nothing in Scala terms. So A or void is just A, and you can go back and forth between those two things. And same on the other side. And then this is also a fun little exercise for the reader, which is to just associate eithers. Okay, I don't think anything here is terribly deep aside from the category theoretic nonsense demotivated at the start. But then we were saying something about monads or monoids in the category of endofunctors, so we need a category of endofunctors. And so what I want to talk about is the category of functors from Haskell to itself. So we had a category which was the category of Haskell data types, right? And where our types were our objects and our arrows were just functions. And here what we want is the category where our functors from Haskell to Haskell are our arrows, and our functors are our objects, and natural transformations, which are basically ways of saying that I don't care what you have inside of that F, like if this was list to maybe or something like that. This would be a function that would take a list of A to maybe A, and it doesn't care what A you have. And you can't do any sort of, is instance of kind of Java e-tricks to do unnatural things. Hence, it's a natural transformation. So yes, Scala is unnatural. So we'll use this kind of squiggly arrow, which you can't really see as squiggly, to denote a natural transformation, which is to say that I don't care what type argument you bolt on there. And so we need a unit for composition, for functor composition, and so you can use the identity functor as the unit for this, because compose a functor with identity is effectively the same as we started with the original functor. We just have some new type noise in Haskell floating around to put on and take off. And then we can put on and take it off. I didn't bother to write lambda, but that's just compose identity A to A, and that's even easier. And then the associativity law is also pretty easy. It's just putting on and taking off some new types. Okay, so now we finally have enough to start talking about a more general notion of a monoid and get to what it means to say that a monad is a monoid in the category of endofunctors. And there will really be a direct application of this to to discrimination eventually. And so now we can talk in a more general setting about what it means to be a monoid. Okay, so we normally just write down that definition of monoid and don't really think too hard about it. But it's an instance of a more general schema. So for any monoidal category where we have our category, we have this bifunctor, which was like product or composition or either, and whatever its identity was, we can talk about a monoid being some object in the category M, such that we have associated with it a eta, which lets us build. This is mempty, basically, or mempty, which will let us take, in this case, the identity of our tensor to M. So this was like unit to M. And in Haskell, a function from unit is boring, so we just throw away the function from unit part of that and just call it M. And we normally curry this definition. So instead of M comma M goes to M, we say curry that, and you get M goes to M to M. And there's all sorts of fun things we can do with that. We're not going to do stuff with that today. We're just going to play with this basic definition of a monoid. And then we work with these definitions. And it gets a little bit awkward compared to what we're used to, because we have to shove these identity elements around. But the nice thing is that this definition, unlike the one that we're used to, generalizes. So now monads can be thought of as monoid objects. Or sorry, monoids can be thought of as monoid objects, hopefully. Otherwise, our generalization wasn't very good. So we start with the category of Haskell data types, with products, with unit. And we say, we'll just use mempty, and we'll uncurry mapen to get the form that we want to work with, such that the monoid laws that we know that we expect hold. I don't think that's terribly surprising. And then monads can be thought of as monoids in that category of endofunctors up to functor composition. So we're using functor composition as our tensor, where if you give me a natural transformation from identity to M, which is to say that you could take an identity of A, which would just be A, to an M of A, for all A, it has to be natural, and so you can't do anything hinky with A. That's our eta, and our mu is that says that if you can take the composition of two M's to an M, you have managed to join your monad. Okay, so this really is the same notion of a monoid, just under a more general definition. Okay, so monads are monoids in the category of endofunctors. Now, what are applicatives then? So it turns out we can build another tensor, something kind of like composition. Okay, and it goes back to this guy, Brian Day, who turned around and did this. And Day convolution, which is not normally presented this way, could be thought of as taking the signature for applicative and smashing in the interesting bits that I want to talk about here, which is that I have an F and a potentially different G. So I have two different arguments. And what I'm looking for is that day of app in the applicative class should take day FF to F. It should be a natural transformation from day FF to F. Right? So if we squint and look at that, and then we sit down and do all the work to show that there's the associator, there's the units, we can actually prove that an applicative is also a monoid in the category of endofunctors, just with a different choice of tensor. We've chosen a different structure to be monoidal with respect to. Just how we could choose either or product when we were talking about Haskell. We could build a monoidal category for Haskell out of either one of those choices of tensor. Here we can build on the category of endofunctors from Hask to Hask. We can build a completely different tensor. So applicatives are monoid objects, and we have our eta and our mu, where we just peel this out and app. Okay. And we just expect the applicative laws in there. Precisely the right laws for day convolution to be, or for this to be a monoid of day convolution. So applicatives are monoids in the category of endofunctors. What's the problem? Okay. Now, I want to play with this definition just a little bit. And the reason is because nothing here required me to pick product or something like that when I went. So instead of using app, what I could do is I could take the definition for like lift A2, which would normally be that I have a function from A to B to C, and then you give me an f of A to an f of B, and I'll give you an f of C. And I could generalize that. This would actually be much closer to what we would traditionally do to build up day convolution in real category theory. But instead of actually building this as a function from A to B to C, what you would normally see is that they'll tensor up these arguments, because otherwise you have to require that it's a closed category, and then I have another 5 incomprehensible slides. And then you could view this as like lift A2 if we uncurried it in the argument here, right? We just tuple up all the arguments we're going to pack to lift A2 and hand them to you. Now, day convolution, if you actually look in any category theory textbook, will not be presented this way. It's going to be presented either like this or using a much more advanced form, which I'm going to completely skip. And this form is a little bit different. So what we're doing is we're saying, now we're going to look at contravariant functors. So how many people here know what a contravariant functor is? All right. I should have, no, I don't. I have a whole spiel after that before I get to what a contravariant functor is. Great. So a contravariant functor is something where when you f-map over it, it goes the wrong way. If you map a function from A to B over a predicate or something like that on a value, then what you can actually do is you can take a predicate on B's and give you back a predicate on A's. It seems totally counterintuitive, but arguments to functions are contravariant. It's the variant stuff that you see in Scala all over the place, the minus signs is the contravariant case. So if you're familiar with like the minus sign in Scala at the type level, that's the same thing. Okay, so I'm often asked, is there like a contravariant monad? No. The little twist that you get that turns you from A to B into f of B to f of A just kind of destroys any attempt at that structure. I'm also asked, is there a contravariant comonad? Well, if there wasn't a contravariant monad, there shouldn't be a comonad, and the answer is still no. But the answer is yes, that there is a contravariant form of applicative. And as a matter of fact, we've got a couple of them we can play with. And we get them by looking at day convolution, the real day convolution, which is normally presented contravariantly, and asking what its monoids are. So what we can do is this. We can say I have a contravariant functor, which I totally did not define. Sorry. Well, other than just verbally right now. And what I'm going to do is I'm going to add I'm going to give you 2 extra operations we can do with it. Instead of just being able to up-map, I want to be able to let you do these 2 things. I'm going to call them divide and conquer, because I needed names. This is, if I turn around and I just take divide and basically do the same trick that I did with app to build the signature for day convolution, I just read this off here and then needlessly alpha renamed things on you. And so we have divide and conquer, which are going to be our 2 cases that we're going to have to consider for our class. And this will be kind of like having to deal with app and pure, or with join and return in a monad, or append and mempty. We're going to find a lot of parallels between these as we go. So, given that class that I just kind of sketched out there, this is basically saying this. These things kind of consume whatever their argument type is, right? So this is like an F that can like handle B's. So this is saying that if you can split A's into B's and C's, or if you can split an A into a B and a C, and you can handle a B and you can handle a C, then you can handle an A. And this is something that says you can always handle every A. You're going to do it in a way that if you divided and just kind of copied the A to both sides, you don't actually change the answer. So this is sort of like a unit for divide. So if you split this thing, you just take A and you just give me 2 copies of A, and you divide using this delta function, and you use some m with conquer as the other side, it shouldn't change the answer from whatever the contravariant functor was going to do. And vice versa on the other side. And then delta, or divide, is associative in this sort of funny way. Okay? So we have this sort of monoid-like thing, which we would expect, given that we're talking about it as a monoid of day convolution. The laws are actually a little bit more messy. because there's nothing that says that this function has to be delta. It can be any function you want it to be. So once you take into consideration all the things it can be, you get this horrible nonsense. So I will spare you from the laws for the rest of these, for this section. But when I picked the choice of tensor here, I picked product and product. I'm taking products in the source category, which is Haskell, Hask-op, to products in the target category, which is Haskell. Nothing forced me to pick product in either case. I could pick I could pick either here, but then that'd be really weird. You have either a function or a value or another value, and somehow you're supposed to handle that and give me back a C. I have no idea how you would use that. But nothing prevents me from changing this one out for a different thing. This one here could be either just fine. As a matter of fact, it's a lot similar to the way that we build up alternative when we get done with this. So we wind up with this sort of class hierarchy in the contravariant world. So we're sort of in bizarro Haskell here. So we have a contravariant functor, f, which says if you can take a's to b's, I can take f's of b's to f's of a's. And I'll have a few examples here in a minute. And we have this notion of divisible contravariant functors, which are the sort of contravariant applicatives. And these are sort of a contravariant alternative. And this is basically saying if I can split A into B and C, and I can handle both, I'm good. And I can always do something that doesn't get in the way. Here, what I can do is this. If I can split A into either B or C, and I can handle each of those cases, I'm good. And if A is impossible, then I'm good. Right? If A can't happen, I can handle it. Lose acts as a unit for choose under the same kind of terms that we built up divide. Okay, so here's kind of a funny thing. Lose is kind of funny because conquer didn't have any argument at all. But if this is supposed to be like pure or return, why doesn't it have an argument? So it seems kind of weird, right? And this one like has a full argument, but we don't have anything that takes like a unit to A in any of the other things or something like that. So why does it feel like this? And I think if I put things in a more symmetric manner, it's much more obvious why this works out. So pure, if we actually work it out in terms of deconvolution, you'd actually get a function from unit to A goes to f of A. Instead of using identity, we would actually be using functions from unit. Because unit is the unit for our monoid, our monoidal tensor. The tensor here being product. The unit for product is unit. Here, the unit for either is void. So we're saying, in this case, a function from unit to A is boring. It might as well just be A. So A to f of A is pure. So we just throw away the unit to part of that statement. Here, what do we have? We have a function from void to A. It takes nothing. It can never be passed and gives you back an A. So we have a function named absurd in Haskell that says, if you've given me nothing, I can give you anything you want. It's in logic, there's a principle called expulso quod libet, or whatever, right? So we can start with this sort of empty-ish thing and say, well, we don't actually need to supply an argument to empty in alternative. That's why in alternative, empty just is f of A with no arguments, no fuss, no foul, just like conquer was. Why did conquer get away with it? Well, here we have a function that goes from A to unit. But unit is the terminal object in the category. So all of these arrows are trivial. They're just the constant function that gives you back unit, ignoring side effects because we're in Haskell. So this is trivial. So both of these middle cases can completely erase themselves. This one can erase this part, but this one can't erase anything because this is nothing special. So that's why lose has an argument, or whether there's an argument to lose. This screwed me up for a long time. I didn't believe this thing could exist until I started thinking about this the right way. Like, I wrote it off for probably 5 years when people just said, is there a contravariant applicative? And I would say no, very pithily, and then I had to eat a lot of crow. So what are some examples of these? Okay, and then we'll finally be able to get to discrimination and put this thing to use. So the simplest contravariant functor that people reach for is the notion of a predicate. It's just a function that will give you back a Boolean given an A. And so you can contramap, you can map backwards over the input to your function. So if you give me a function from B to A, I can compose it onto your function from here, and you'll get a function from B to bool. Divisible for predicate is interesting because conquer, I'm going to choose to, I have two choices of monoid that I can use on bool that are easy, right? I can use and or. What's the unit? Well, if I use and, I better use true. If I use or, I better use false. So conquer should be the unit for divide. It just says, yes, this is true. It's a valid predicate. You can apply to anything you want. And then divide says, take my value, A, split it up into B and C, test both predicates, and add the results together. Not terribly terrifying. On the other side, we have to say, well, if A couldn't have happened, great, it didn't happen. And then here we have to say that if you can handle either of the two cases, figure out which one of the two you have and dispatch to it. That's a predicate as a contravariant functor with all this extra structure attached. All of these pieces actually work out as fairly common sense things you would expect to be able to do. The motivation for them is somewhat Baroque. And in general, if you have anything like A to R, where R is some monoid, you can do the same thing. You can just append the two results. You can use the unit for it. Absurd. Nothing here changed from predicate except a couple of symbols. Now we might get more interesting if we have more than one A in contravariant position. An example would be the way that we might build a contravariant functor for talking about equivalence classes. And that is that you're going to give me a function from A to bool, which should be symmetric and reflexive and transitive and all the nice things. Those are the nice things I guess you want out of an equivalence relation. And then we need to be able to map over both of the arguments. You apply the function on both sides, and then you apply the original the equivalence class. We divide by splitting each of our arguments into the pairs, and then testing each one of them to see if they're equal. And then you're equivalent in the sort of product equivalence class. Here, choosing is a little bit tricky because you have to actually check to see that they both kind of got shoved into the same equivalence class. You have the sum, the direct sum of two equivalence classes, or two families of equivalence classes. And you disagree if you're in different cases. We can do comparisons. We can do things for ordering. And by the time when we get done with this, the whole point of this is that discrimination will wind up being generalizations of this approach and the previous thing, just using much more machinery. And so here what we can do is we can divide into the two cases, and then this will build back, this gives back an ordering, which is either less than, equal to, or greater than. And the monoid for ordering smashes them together, takes the first one if it's not equal, and if it's eq, then it takes the second one. And so to conquer, we just say that it's equal, and we don't do anything. And then we split into left and right cases, and lefts are less than rights. And then you agree with what GHC will generate using the derived instances for eq and ort. All that kind of fun stuff. Okay, so continuing down the rabbit hole, how many people here are familiar with GHC generics? All right. So in GHC, one of the things that we can do is we can say, given whatever algebraic data type you've built up, we can say, how does it break down into sums and products and leaf level things, okay? And so this is sort of the product case that we see there. This is the sum case that we see there. These things are functors, and I'm skipping a bunch of cases. But we can basically see that this is basically borrowing the power to divide to handle the products, borrowing the power of choose to handle the sums, and saying, okay, the rest of this goes out into the GHC generics machinery. So no matter what data type you have, what I'll do is I'll look for some constraint Q on the leaf level data types that I have in there, And if for anything that I have this constraint on it, if I can give you back some decidable functor f, then I can build up an f for this whole result in a generic way. And then we do some boilerplate and wrap all this up, and we get this class, or this data type here. And so you can just completely ignore that slide if it was too opaque, and just say that we have this function deciding that says, you tell me what constraint you expect, in this case, ORD, and you give me a way that says, given that constraint, I can give you one of those contravariant functors. So in here, comparison is the data type that we built up before for talking about comparisons. Compare is a function from A to ordering, or in this case, B to ordering. So we package that thing up, giving us a comparison on B's. This is telling the generic machinery, hey, walk through whatever structure you were given all the way down to its leaves, and as long as every single one of those can be compared, we can compare the result. And this gives you a generic comparison function as long as those pieces hold. So for whatever data type you happen to build up. Here we can do the same thing for equality, because A to bool, the equal function, gives you back an equivalent, a form of equivalence class. We have to feed it the proxy to tell it what class constraint to use, but other than that, this lets me get rid of writing a whole crud ton of GHC generic code when I just need to consume a data structure and look at it as sums and products. If I needed to do more and needed to know the constructors or something like that, I'd have to do something more exotic. But I can put this in the contravariant package, and it just works for everything that I happen to care about. Okay, so now that we have all of this machinery, we can go back to the very simple API that was built by Fritz in his original papers. So he built up this notion of what he called a stabled ordered discriminator, and then he built this data type. And the problem in many ways with this data type is that I have no classes that I can put on this that I can obey any real laws for. I can make an instance of contravariant by putting map constructors on everything. But that's pretty wonky in the sense that I have to change the shape of the data type to put a map in the front of it. Now I could put one of these kind of functions in the front of every single one of these things and then play games with the innate lemma and do all sorts of horrible things to make that perfectly legal. But then I wouldn't be able to talk about sums and products and dividing and conquering and all that other kind of stuff, where I had nice laws and nice units and all the things to make it go. So I want to replace this data type with this data type. And so what we're doing here is this. I'm saying, if you give me a list of pairs of A's and B's, what I want you to do is give me back a list of B's, where these are the individual equivalence classes that you found over here by whatever criteria, by hook or by crook, you wanted to pick out of A. Not my job to figure out what that is. You have to give me back all the B's, and the inhabitants of your individual equivalence classes should be given stably with respect to the order that you see them here in the input. Those are the constraints I'm going to put on you. Anything that you can implement that is subject to those constraints is a valid discriminator, a valid stable ordered discriminator. And so you should only be using the value of A to figure out what you want to do. So this is a contravariant functor. You can contramap over it. And I can build a class, let's call it sorting, for things that we can sort in this fashion. So assuming that I can build divisible and decidable for this, we can use this class, and we'll just say, hey, by default, use the generics to walk down to leaves, and as long as you can sort the leaves, you're good. So any tree-like structure, we can just borrow the ability to handle all the leaves and let the generic machinery walk up the tree. And so now we can handle the empty case, booleans, lists, maybes, whatever, assuming that I have divisible and decidable. And the law that I want for this is that if you give me any strictly monotone increasing function on f, it shouldn't change the answer. So this is sort of me requiring this thing to be a structural ORD which is perhaps a little bit overshoot on my behalf. You know, we have ORed instances that are not purely structural. But so be it. This is what I want. So I'm claiming it. My library, damn it. Okay, so now how do we do divisible? Well, we need a conquer. So conquer has to take this thing and give me something that doesn't muck up the story. So it has to build one gigantic equivalence class and shove all the crap in it. We just say, you gave me a list of A's and B's, that's nice, drop the A's on the floor. Now I have a list of B's, and I'm going to give you one equivalence class, so I'm just going to return a single list that contains one list inside of it, which is all of your B's. And then if you have two ways of sorting your numbers, if you have like a way of breaking things down into, if you have the ability to sort B's and you have the ability to sort C's, then what you can do is this. You can start with your A and whatever it's carrying, let's call it D because I didn't want to deal with B twice. We run through your list, we break it out into pairs of A's and D's, where D's is the payload, the thing that you're actually carrying around that you're going to leave in the end. Then split the A into B and C. Now reshuffle your payload, so it's a product of B. You're now using B as the thing you're going to discriminate on, giving you C's and D's inside of it, which we don't care about because we're just going to pass it through. Discriminate, using the fact that L is going to do the stable discrimination on that. And then bind to R, which is going to do a sub-discrimination on each one of the individual pieces. And by the time we're done, we'll have broken things out into an equivalence class for every sort of product of the two equivalence classes that we wanted to deal with before. And it will be stable, and it will sort. So we just dealt with products. And we can deal with sums by saying that if something can't happen, well, it's never going to come up in my equivalence classes, so I don't need to worry about it. And in the other case, what we have to do is sort of break things out into lefts and rights. So all we're going to do here is we're going to pattern match and say, hey, take all the lefts here and run them through the left discriminator, and then append the result of running all the rights to the right discriminator. So we put all the lefts before all the rights, which is what you would expect if you sorted either A, B, a list of either A, B's. So we have now dealt with sums and products, but we haven't done any radix stuff. So I'm just going to punt and say, hey, look, you can do a radix sort for sorting that, which says somehow I'm going to give you n buckets, go through, shuffle all the data into those buckets. You can do it using array or vector, whatever you want. And then we just won't use this for big numbers. We'll use it for like 65,536 or less, say. So for word 8 and word 16, those are easy. And then what we can do is build up this sort of notion of using an American flag sort by breaking things up into the least and more significant bits and then running it through the engine. Now, this is the approach that Fritz takes in the paper, but where I was talking about how American flag is sort of top-down and radix sort is bottom-up. So American flag is going to do lots of little sorts, and radix is going to do an enormous set of sorts. It's going to sort everything, however many times you have, sort of. I can take this and drop this into a radix sort, which is basically go through, break these things out into the least significant bits, then the more significant bits, and then keep the original answer around as a tag. Then I can run through this thing kind of the wrong direction using binds to glue the whole thing together. And when I'm done, all I have to do is sort of gather these things up into runs where they agree on this key. Okay, and that can be done fairly quickly, actually. And the nice thing is, well, those things are words, so this is just comparing words to do the join. This takes the same asymptotics as this, but the constant factors are ridiculously better, despite the fact that American flag sort was designed to work around the constant factors of radix sort. The benefit comes from the fact that we do far fewer individual sorts, even though we're doing bigger ones. And so I use this for my number types, but then I American flag all the other pieces. So it's sort of a hybrid up, down, top, bottom, all over the place kind of sort that has the right properties at every given step. And so the nice thing is when we're done, we can take our sorting data type, our sorting algorithm that we've just built up for whatever data type we have, A. We can run it. We'll feed the data type itself as the thing we're discriminating on, and we're carrying itself as the payload, and spit out the answer, and this will sort a list in O(n) time for any data type that we can run through. So any algebraic data type that happens to contain numbers or other algebraic data types will work. And we can do sorting with, if you want to do like the Schwartzian transform trick, you know, thank you, Pearl, where you prepare it with the key so that you don't have to pay for an expensive key calculation over and over again every time you walk through the list. We can just do that. We're building a list that has the key and the thing that we want to work with, and we go. So that's also O(n), as you would expect, but it fits very nicely in. So you can see this is just the Schwartzian transform with the identity function. Now, in data.map and data.set and these different container types that we have in Haskell, we often have a fast map construction that runs in linear time if you promise me, you know, on your mother or whatever, that the inputs are in order. So if we require that our sorting agrees with the order that we get from ORD as an extra law, then you're perfectly able to say, sort, putting all this stuff in order. Now you have a bunch of equivalence classes. Take the last inhabitant of each equivalence class, because that's what toMap is going, or what from list was going to do, and then feed them to this from distinct ascending list thing that's linear time, and we just constructed a map in linear time rather than n log n. So anytime you're going to call from list with or from list, consider that you can use this discrimination stuff with another instance, and that instance is going to cost you one line worth of code and will be automatically generated for you. Okay. So we can win on constants for map construction, set construction. You know, those don't come up in functional programming at all. So that's kind of nice. So far what we have is O(n) stable order discrimination on any ADT, radix sort instead of American flag sort boosts my constants, and then GHG generics let us derive the instance. We had to use a lot of theory to get here, right? We had to go off and find what are the monoids of day convolution, but we got a nice API, and we're able to use these nice classes that have applications in all sorts of other domains, and we can directly see the connection in many ways to sorting and grouping, or where we had the equivalence classes and the ordering. Which then invites the question of, what are the things that I can only compare for quality, but not order? And how could I gain anything here out of that? So here's Fritz's solution. Now mind you, it's absolutely brilliant stuff that he's got here. We just want to get to there. And this is actually, I'm going to show that this is actually probably wrong for unordered discrimination. I'm going to show the problems that we're going to run into, and the problems that in many ways you run into if you take Fritz's papers at face value, which actually really surprised me. Yeah, actually, a really horrible anecdote that will probably get me tarred and feathered is that when I was working on this stuff, I was realizing that I was doing a talk on discrimination, and that my solution for discrimination was to use the final solution. And then I realized I was going to go from here to right next to Germany and give a very similar talk, and I realized I had to do something to walk it back. And so fortunately, I found that there's a bug in Fritz's paper, at least a subtle issue that I want to take up with Fritz's paper, so I could say that discrimination is wrong. Please take that away as the takeaway. And greatly redeem the subject matter of the talk. But it was touch and go there for a while. So here we have our notion of grouping that we want to work with. And where might these come up with? Where might these come up in practice? Well, IO refs have an equality instance. You can compare two IO refs for equality to see if they're the same pointer, the same thing that's pointing off to whatever it could be pointing off to. So if you have the same object in memory that, like, when you change it, will change all of the other members that compare for equal in the IO ref, right? But it doesn't have an ORed instance because we have a garbage collected system and everything slops around all over the place in memory, and we're not just market sweeping, we're actually, you know, compacting or two-space collecting or whatever we're doing. And so that's one case where unordered discrimination can really matter. And the other one is that we can show that sorting is is provably unproductive. If you have to sort a list, I can't start giving you the answers until I'm done sorting. I have to see the whole list, right? And so if I'm interested in doing joins or a bunch of other things, and I want to be able to start giving you an answer immediately, I'm stuck. The moment I require any form of sorting, I'm dead in the water. I just can't do it. But grouping has the potential to be productive. So we can build a, a horrible combinator here that will do a modified radix sort. And what I want to do is this. This is kind of terrible. So the obvious way to make, you know, high-performance functional code is to use unsafePerformIO to do things. We use unsafePerformIO inside of unsafePerformIO because that, you know, we weren't getting enough speed out of one. And a couple of unsafe choruses just for good measure. And the idea here is this. What I want to do is, when you tell me the number of buckets you want, I'm going to make little arrays that are going to act as a pad of that size. And I will leak as many of them as you ever use concurrently, but I can bound that by the number of active contacts. So it will actually be a fairly small thing. You'll leak a meg or something like that, and you'll never get worse. Then what I'm going to do is I'm going to make a sort of a mutable, really, but I'm not going to tell you that it's there, reference that holds onto a list of these arrays, these vectors, where for each one of the cells I'm going to put in whatever I want in there. And I'm going to, before I'm done with this array, I'm going to restore it to pristine state. I'm going to give you back an array that's all empty lists. And so that's justifying the fact that these are going to be any's, because by the time you see it, you won't be able to distinguish that it once held something else. And we're going to run. And then what I want to do is go look at this list and see if there was something on the free list that we could take. And if there is, give it back. And if not, don't. Here, if you got something back, use it. Just cast it, change the type, do the horrible things. Yes, it's awful. Otherwise, build a new array of the right size. Go through, and what I want you to do now is run through using your array of t-value pairs and look at the appropriate bucket. And if it's empty, add the key to a list of buckets we've now seen. And then thread the answer or the element into the appropriate bucket. Right? This is the bucket, putting the thing into the buckets of a bucket sort of a bucket sort. But what we're doing is we're keeping track of the order in which we encountered the buckets first. And so if we encounter a bucket we've already seen, we just put it on there and we don't thread it onto our list. When we're done, we go through the list that we just built up in the appropriate order. We read, we reverse the lists to get everything stable, blah, blah, blah. We scribble out the empty list in. We scribbled an empty list into everything that we actually used. And we got out our stably sorted results. And we smash that array back onto our free list when we're done. Now, why did we go through all of this effort when we could have just made whole new arrays, right? Well, these arrays are big. They can be like 65,000 entry arrays with, 8 bytes per pointer or whatever they're going to hold. They can be fairly sizable, and the cost of initializing one of these arrays from scratch is much higher than the cost of going through and touching the handful of cases in it that I actually used and banging back in the empty list. Okay, so this actually takes this thing from being about 6 times slower than quicksort to being 2 or 3 times faster in many ways, in many places. So it was worth the horror because it had to win or it was useless. And so Fritz did something very similar, but he just made he didn't have the free list and so it just created race hazards. So this is a slight modification of Fritz's approach to get rid of the hazards. And so the grouping law that I would like to have is this. If you give me any injective function, then contramapping that function over grouping should just give you the same grouping. So what I want to do is I want to give you back the equivalence classes in the order in which I find them, the order in which I find the first inhabitant of the equivalence class in your input, not in any order that is determined by the elements themselves. So I'm not sorting with your data. I'm using your data to discriminate whether or not two things are equal, and then I'm giving you back your equivalence classes in order, in the order that I encounter them. So why this law? So with that law, we can build a number of really nice functions that could theoretically be completely online. We could build a group that would go through and allow you to just say, find all the things that are the same and dump them into equivalence classes. And we could possibly lazily produce each one of these sublists. Like as we're going through consuming the input list, we're continuing to spit out more things on the end of each one of those target lists. Okay? It works out domain theoretically. Implementing it is equally horrible to the things that you've seen so far, or worse. Nub is ON squared in Haskell today. Here we can do a nub that doesn't leak n log n space or whatever like we have to do today to do an efficient nub with a set, but we can do a nub that is ON by using grouping and taking out the head of each one of these lists, because the moment we create the list, we put its head in, and then we move on, and then eventually we're going to put more stuff into it. But it could be done productively, where you can get access to the heads. So this gives us a number of functions that we already have in Haskell today. Group in Haskell we have in ON, but we only allow you to group neighboring elements. This would let you shove things into a group much, much later, which is a different function, admittedly. But the names were chosen because then they work with, there were a bunch of link-style extensions that Wadler and some folks smashed into GHC at one point that I don't think anyone's really used since. But this would let you use all of those list extension comprehension-like things with grouping instead of having to pay to do full sorts for everything. And the key here is, again, we have this potential for streaming. So if we had something where we're like grouping integers, we're going to see that the first group starts with an A. I don't know how many elements it has in it. I don't know how many other equivalence classes it is. But the moment I've seen this element, I know that I have one equivalence class and it starts with A. The moment I see this element, I know that I have another equivalence class and it starts with B. The moment I see this element, I know that the first thing that I saw, or the other equivalence class, now has an extra element in it. So as I'm going, I'm gaining information, sort of LVAR or IVAR style. So you can see how implementing this will be horrible. But there's a potential to do fully online streaming of nub and all these other operations and still have this linear time guarantee. And so we come into trouble with the law where in the actual original discrimination paper, the implementation for handling sums looks a lot like the way that we handled them for sorting, because it is sorting. And the way that we handle products looks a lot like the case we were handling for sorting, because it is sorting. And so this is, why in many ways discrimination is wrong. Not the perhaps much more timely social message, but the why this particular library has a problem with the concept of discrimination, and that is that we shouldn't be sorting here because it's destroying that law that I wanted to put in, that contramap F of grouping is grouping whenever F is injective, which is effectively saying that the only source of information that we have is the order in which we encounter the equivalence classes. Okay, and so both of these cases are wrong, as is that grouping nat thing, that beautiful thing that we had with the two nested unsafePerformIOs. It's not sufficient to the job. So there's a fix. We can make a version. If you give me a grouping that isn't legal, I can enforce it to be legal by going back to using sorting. This will totally never give me productivity because we've already shown that anything that needs to use sorting can't be productive. An example would be if let's say that you were trying to use nub by sorting, and you were going through and you were just given an infinite list of trues, right? You have no way of knowing that you won't get a false, right? So you can't tell me true because false is going to come before the trues that are going to come out in your output list. So you're just stuck waiting for a false or an end of list. So you just can't make progress on the output no matter how much more input you get until you see false. Here what we're doing is we're saying you had some grouping you wanted to perform. What I want you to do is tag every element that you're going to do with its element order in the original list. So the payload, instead of being whatever B you were going to carry around, is now an integer and that B. The grouping that you're going to do does whatever it's going to do to break things out into equivalence classes. It might partially sort, it might do whatever. But when it's done, you have a list of lists where each element in there is an integer and the actual argument. And so what we can do is we can peel it off. We know that the internal ones are non-empty, get out the n, sort by that n, and then peel out the value from it. And that's horrible, but it actually does get you a legal unstable discriminator. Yes, I realize I'm pushing really hard to sign. So how much can I run before you really want me to stop? Hard. All right. Okay. So we can fix sums productively by doing that same tagging trick. And by working here, this actually has a productive story. We can do discrimination on pointers, which we know we can't have an ordering on, by going through and saying I can discriminate on addresses. So you give me a list of pointers, and what I'm going to do is I'm going to build a custom foreign prim, which totally does not work on the screen, and then force this whole list and go out onto the heap and do horrible things to walk this thing manually behind the scenes. And with that, I can actually sort lists of IO refs, or not sort, I can group them into equivalence classes in ON time, even though doing pairwise comparison, you can't do better than theta n squared. It just can't get better, right, with pairwise comparisons than that. Sometimes we don't care if it's sorted or not. Like for joins, I might want to be able to join on an ordered predicate or not. But you can do joins just by showing that what we'll do is we'll inject it on, we'll make our payloads lefts and rights. So you have two things you want to join. You'll have like one table on the left and one table on the right. So we'll inject whatever the thing was to tag whether it came from the left table or the right table, append these, run them through my discriminator. I'm going to get however many equivalence classes, and in each one of them I'm going to have all my lefts before all my rights. So I can just take all the lefts, then deal with all the rights, take the cross product within each one of these sections, and I'll spit out the result, and I will take no more time than it takes to touch all the inputs and all the outputs. So that's the linear time join. Implementations. And then the key here is that what I'm looking for is this notion of a productive, stable, unordered discriminator. Okay. It needs a better version of grouping net. It needs a better version of divide. It likely needs a different encoding. It does look promising that you could do something with like a custom ST-like calculation that can produce lazily driven IVARs or something like that. But ultimately, discrimination gives us a whole bunch of things in ON for a whole bunch of different types that you wouldn't expect. And the code is online. I'll throw it on Hackage as soon as I actually can resolve that productivity argument, or as soon as I give up. And help me get there. So, thank you.